I am Nicolas Thome from CNAM at Paris in the Cédric laboratory in the statistical learning team. And I will talk this morning about going beyond full supervision in deep learning. And I will start my talk with some slide of context, just to remind you the huge success that deep neural networks have been witnessed in the last 10 years, let's say. And especially the big success that has been witnessed for image classification at the ImageNet challenge in 2012, where deep convolutional neural network show outstanding performance for image classification in these data sets. So here, just one slide to remind the performances, the numbers. So the approach winning the contest in 2012 was based on deep convolutional neural network, AlexNet, and it enabled a big gap in Svm performance compared to previous approaches which were based on a handcrafted representation of image and let's say shallow machine learning models such as super vector machine. Okay, and just also this arrow to illustrate the fact that deep neural networks are pretty old models that date back to 30 years ago, and that have known a period of success and decline. And so, okay, now for 10 days, there is a very big renewal on the use of this model for visual recognition in particular. So, there's first two main reasons for the recent success of this deep convolutional neural network model, and especially in this large-scale recognition challenge. And these reasons are essentially practical, meaning that the very good performance obtained by this model essentially comes from two aspects. So firstly, the huge number of data, and especially of label data, which enable to train very large models without too much suffering from overfitting. Okay, and this is one of the main aspects, and this is also one of the main strengths, let's say, of this ImageNet dataset, which contain more than 1 million labeled images and about 1,000 classes. So both these two numbers, the number of labeled images, the number of classes, was really the main reason which makes very large model able to learn meaningful representation, and which explains the fact that these models were not able to work for 30 years and have been successful since this date. Okay, and of course the second reason is the use of specific hardware for implementing these models, for training this model, and in particular to a graphical processes unit that enable to significantly reduce the required training time for training this model, which remain still computationally demanding. For example, for training this model in 2012, it requires about 1 or 2 weeks for training the model. But the optimization time due to the GPU enable a speed up which is between 1 to 2 orders of magnitude, and it's really unable to the widespread use of these models and the ability to train this model in a reasonable time. Okay, and one key component of this model is their ability, compared to, let's say, shallow deep learning model, is their ability to automatically learn representation from data. So you don't have to handcraft your feature at hand for a given task. And the model, from label data, the model is able to learn representation. And a second aspect I'm going to talk about today is the notion of manifold untangling or disentangling, which is terminology borrowed from the neuroscience literature, and which basically means that perceptual systems are able to disentangle data manifold in the sense that when you look at raw data, input data, they are somehow very noisy. For example, in this example, if you look at this video sequence and you look at each pixel intensity and you look at its variation over time over the sequence, it will give you a function which is very noisy, which very fastly. And on the other hand, if you look at some high-level representation of the scene, such as object identities, they are relatively stable over time. For example, in this video on the left side, a monkey is present. So this object, this animal is present for one time on the video, and then it disappears. And so at this high-level representation, object identity, we have stable representation. And if we looked at that data in their input space, and generally for many machine learning problems, we can imagine that the data manifold is really tangled, meaning that for a given set of class, so for example, imagine you have two classes represented in blue and red here. If you look at the structure of the data manifold, it's really tangled. And what perceptual systems are able to achieve is really to disentangle this manifold such that at higher level of the representation of the data, you are able to disentangle this manifold and to discriminate the class with simple models, simple linear models. And this is also one key aspect of this deep learning model, which show their ability to gradually disentangle the data manifold, so to automatically learn feature space, which are able to linearize deformation, so that at a given stage you are able to classify model from the learned representation with linear models. So, just to give you an illustration of that, that's I think a nice visualization of this manifold disentangling capacity of deep learning model that I did in practical session, and that I think it's meaningful. So just as an illustration, just consider a very popular data set in vision and learning, so the MNIST data set, which is a handwritten digit data set. And let's say that we want to analyze the structure of this data set in the input space, so in the pixel space. So, okay, you have images at about 30 times 30 pixels, so you have somehow a vector of time 900 as input. And if you look at the structure of the data in this data set, in this manifold, you will have something which is very tangled like that. And to visualize that, you can just try to project each image, so each input vector of this size, one vector of type 900, and to project in a low dimensional space. So let's say 2D or 3D using a visualization technique. So one of state-of-the-art visualization technique is t-SNE method, okay, which project one data point into a 2D vectorial space. And if you look at the structure of the different images with each color code representing the class, you can see that there still is a structure and the class are a bit separated, but there are still overlap between the class. And now if you train a convolutional neural network or a fully connected neural network to classify digits, so to perform classification on these 10 classes of digits in this data set, and if you perform the same visualization task but from a latent space learned from the network, we can see that the classes are much better separated. So that is what is shown in these two projections. So in the center, it's the result of the projection from network, which is a fully connected layer, and the right side projection illustrates what is learned from a convolutional neural network. So it really shows you that the capacity of this model to learn representation space, where when you look at the data structure and the class representation in this representation space, you are able to better separate the classes, and so somehow perform this data manifold disentangling task I was mentioning. Okay. And so now, as I said, there is big success of this deep convolutional neural network for classification. And one open issue at the time of this success was, do we need to connect a very large-scale, huge-scale dataset for each task at end, which is, of course, very costly. And for example, for medical image analysis, we need to collect ImageNet scale dataset for achieving such results. And one first observation was indeed to prevent from doing that, we can transfer representation which are trained in large-scale datasets, for example, in ImageNet, by simply using pre-trained neural network that have been optimized for classifying classes in ImageNet, for example, and use this neural network as feature extractors. So that is when it's shown here. Imagine you have a medical image, and then you apply a convolutional neural network that have been trained on ImageNet, and then for a given image, you just apply the network and keep layer activation of the network. For example, it could be this fully connected layer activation. Here, this is an architecture from a VGG network, which won the contest in 2014. And then you use this feature just as image representation. And then, on top of that, you can use any machine learning model, which has, let's say, few parameters and can be trained robustly in small-scale dataset by leveraging these deep features. So, okay, this kind of strategy, so transfer learning from model pre-trained as ImageNet, is nowadays, let's say, the standard approach when you want to handle any visual recognition task in natural images. Okay, and this strategy reveals also to be pretty robust to large domain shift, and for example, for medical images. Meaning that if you use this kind of generalist feature that have been trained on ImageNet for distinguishing the 1,000 image classes, the learned representation proved to be effective as well for representing medical images. And they are used and they have been used in several contexts, for example, as initialization of network for polyp detection, and also more recently for contest winning the liver and tumor segmentation challenge in 17. Okay, and that's let's say this transfer learning and eventually fine-tuning approach is one baseline approach for any visual recognition task, as I mentioned. And what I'm going to talk about today is how we can build more complex machine learning on top of that. Again, noticing that data labeling is very expensive, and that the difficulty and the challenge is exacerbated in the medical context, of course, because labeling data in medical images require a strong level of expertise, which is not the case for natural images, for example. So I will talk about two kinds of methods to handle smaller scale data sets. So methods which are based on leveraging coarse annotation. So what I mean by coarse annotation, for example, is just having a global label on an image, but in the goal of performing more precise or accurate tasks. For example, you have a global label in this image. You only know that a cancer, this is a cancer or non-cancer image, and you want to perform localized tasks, such as identifying the presence, the label, or putting the label cancer or non-cancer to each region of this image. So, for example, for performing localization or segmentation at the pixel level. And a second kind of approach I will discuss are methods that try to leverage the lot of unlabeled data that we have at our disposal, in addition to a subset of a few labeled data to improve model performances. Okay, so I will start with learning with weak supervision. So again, just to fix the idea, using full precise annotation is pretty costly, and especially when you have a very, very accurate labeling. For example, bounding box, or even more if you have segmentation mask, again, labeling at the pixel level. Here are a graph just to illustrate that. So just what is shown in this graph, in blue is the time required to label an image at the pixel level, so it takes about more than 1 minute for a human. And at the global level, so at the global level, you only need, for example, 1 second to label one image, about 1 second to label one image. Okay, and in red, what is shown is the number of images available in public dataset. And of course, what we can notice is that there are about 30 million, let's say, public dataset with global image label, and about 200,000 public dataset with image label at the pixel level with a segmentation mask. So this clearly motivates the fact that it would be very interesting to leverage the huge number of data labeled with coarse label, for example, with global label, to perform on the other hand, more challenging tasks and accurate tasks such as image segmentation. And again, the problem is exacerbated in the medical domain, because we have very high resolution images, which again makes the pixel level labeling more expensive. We generally have 3D, we might have 3D data on video, which clearly make this segmentation as a pixel level not practical. Okay, so one problem I will focus now is really this problem of having at one disposal a set of image with global label, for example, this image at the right with a cancer label, and try to perform more accurate localization tasks, such as localizing regions that are responsible for the global label, or even segmentation at the pixel level. Okay, and I will detail a very popular model for weakly supervised learning, which is multiple instance learning, and which is a very old model, let's say, which has been proposed more than 20 years ago. And the model formulation is the following. You consider a given input data as a bag of instances. So instances are subpart of the data. So that's a very general model, which have been applied to several types of data beyond images. So just to mention that, you can apply it to text. For example, if you have a text document is composed, for example, of paragraphs of sentences. So the bag would be the whole text, and the instance of the data would be the paragraph composing the whole text document. It can be applied to, for example, to any sequential data. For example, molecule. You have molecule, and you want so the bag is the whole molecule itself, and the instance are subpart of this molecule. And this kind of model has also been applied in this context to localize in the molecule which are the area which are responsible for a given molecule property, for example. And if, of course, for an image, you have the bag, which is the image itself, which is composed of a set of instances which correspond to different image regions. So, for example, here is this image. You have the whole image and 3 regions that is shown, and here the same thing for these natural images. Okay. So this is the general formalism, really, which is based on this bag of instance. And of course, to perform prediction, you have to describe somehow your data. And here we assume that each instance, so each region in our case for images, is described by a feature vector that we denote as phi, depending on the bag B, and H denote the image region. So, for example, in this case, we assume that there are NB image region in our images. And so each image region will be characterized by a feature vector in a vectorial space of D dimensions. So it can be simply the raw pixel intensity. You can choose handcrafted feature, or you can choose deep feature, as I mentioned, which correspond to the activation in each region of any of your favorite deep convolutional neural network. Okay, and once you have this feature space which is defined for each region, the problem, the multiple instance learning formulation is formalized as follows. You have a set of training example, training pair. So for the highest training example, you have the bag and its label. Okay, so just for simplification, let's assume that we are in a binary classification problem. So you have two-class classification problem. So the label will be +1 or -1 in this case. For example, if you want to discriminate concert from non-concert images in this example. Okay, and the main point is that in these multiple instance learning models, the supervision is weak in the sense that you have only a label at the bag level and not at the instance level. Okay, and the main challenge, the main goal is, at the end, the main objective of this kind of model is to be able to perform prediction at the instance level from this global label. So this is, of course, a learning task which is more complicated compared to standard supervised learning. So in standard supervised learning approaches, you have a label for each data point, and you try to find the model which minimize your classification or error over a training set. But here we have only a label at the bag level, and we want to perform prediction at the instance level. Okay, so to perform this task, so to be able to train a model from this global annotation and to perform prediction at the instance prediction, we need to pool information somehow, so to aggregate information somehow, so that at the end you can have a prediction at the bag level from your model that you can compare to the ground truth label which is provided during training. Okay, so that is one of the key aspects I will detail today. So what are the main approaches for this pooling and aggregation strategy? So one option that has been explored in the multiple instance learning literature is to pool at the beginning of the process, let's say, over instance features. So as I mentioned, you have a given image regions which are described with feature phi. So let's say you have n feature for your image. Each of one is a vector of d dimension. And one simple strategy to have to be able to train your bag of instance from global label is to pool the instance feature. So with a function g, the function g which is the pooling function, and by applying this function g, so I will give some example later, but basically at the moment let's imagine that you have a very simple pooling function which can be an average or max pooling. It gives you a vector from a set of n feature vector representing describing the n instance in your bag. You build a single vector of a given size, d prime, for example, and on top of that, once you have aggregated your instance descriptor, then you are directly able to train your model from the global label, and then by doing so, we are back again to the standard supervised learning problem because we have a single vector for each bag and a single label for each bag. So this is one solution for this problem, and one drawback of this approach is that it is not straightforward in the general case for any pooling for a function or classification model to perform instance prediction, because you have pooled in the feature space, and now to really have a prediction at the instance level, it's not straightforward. So I won't give more detail about this kind of approach, but there are important, there have been intensive exploration in this direction in the multiple instance learning literature. So on the other hand, the other approach is directly to define a predictor at the instance level. So for example, for each image region in your image. So you have your 5 features which describe each region in your image, and then you define a prediction function, FW. So again, if we are in a binary classification context, you can just imagine that this prediction function will output a single real valued output, which sign will enable you to classify your region as positive or negative. Okay, so you map this d-dimensional vector to a single real valued vector, and it provides you a way to classify your region as positive or negative. And then once you have your prediction, your decision function at the instance level, we can pool or aggregate over prediction instance score to get the final bag prediction, the final image prediction in this case. And then on top of this decision, again, which is in this case, in the case of binary classification, which is a real valued function, we aggregate this real valued function with a function g, which again can be average or max, and I will discuss about that later. But it gives you your bag prediction, that I denote y high hat, which is a prediction of your model, that you will, at the end, ultimately compare to the label provided by the supervision, the ground truth supervision for your image. Okay, and so this kind of approach have been implemented with a popular algorithm based on a super vector machine in the early 2000s. For binary classification using simple models, so using linear prediction model on instances, so meaning that you have your d-dimensional vector phi, and you simply complete the dot product in this vectorial space with parameter w. So you have a linear predictor in a given feature space, and using a pooling function which is based on max pooling. So once you have, for each instance, once you have computed the prediction for each region in the image, you compute the bag prediction, the image prediction, by taking the max over instance scores. And just looking at this sign, the sign of this max scoring instance, you classify your image, your bag, as positive or negative. Okay, so this is one of the most used, let's say, multiple instance learning prediction function that have been used in the literature. So it's at the prediction stage, and several variants during training have been proposed with this SVM mill algorithm. Some of them so I mentioned 3 of them, which are the most popular variant. So what is shown in these 3 variants are 2 bags, one positive, one negative. And the difference between the 3 training variants that have been done is how many instances you use in bags for training. So in latent SVM, so you have these 2 bags, and you only use the max scoring instance for positive and negative bags during training. So you characterize each bag only by the instance, which gives you the maximal score. In big MI SVM, you use only the max scoring instance for positive bags, but you use all instance for negative bags. And the rationale of that, I forgot to mention that, is based on one of the most important multiple instance learning assumption, which is that when, as you have your labeling at the bag level, you assume that for negative label, for an image with a negative label, you assume that all your regions are negative. So for example, if you have this cancer image, if you have a global label which is non-cancer, you assume that all regions in the image will receive the label non-cancer. And on the other hand, if you have a positive label at the bag level, you assume that there exists at least one region which is responsible for this global label. There should be more than one, but there is at least one, and of course none of them are supposed to be positive, because in this cancer image you can look at several regions that doesn't look like cancer. Okay. Okay, so this is a big MI, and the small MI again is a small variant which use all instances for a negative bag, but also all instances for a positive bag. But as you don't know the target label for positive bag, the algorithm attempts at relabeling, automatically relabeling each instance in positive bags. So you try to optimize the model such that it automatically provides you a label for each instance in the positive bags. For example, during training, the algorithm will tell you that this green area is a non-cancer region and that these two red ones are cancer regions. And of course, this supervision is not providing at the beginning during training, because you only have the global label which is providing at the image level. Okay, so this kind, just for an historical, let's say, recap, all these SVM-based multiple instance learning algorithms have been applied in a different context, but for part-based object detection, which lead to a very famous model for object detection, which is a deformable part model, and which is really based on this multiple instance learning algorithm, which is an instance on the big MI SVM algorithm that I mentioned in the previous slide, and which have been adapted in the context of object detection. And in this context, what you have is you have a supervision at the bounding box level. So for example, here during training, you know that in this image, a bicycle is present in these red rectangular regions. And the supervision is weak in the sense that the model attempts at predicting subpart position of the region, which are shown in blue here, which try to automatically adapt to the visual content of the image to better localize the object. So here, the latent variables, the instances, are the part position of the object that you optimize to better align your model to the visual data. Okay, and in this work, okay, input features, so the visual feature that have been extracted for each image pair parts have been based on a handcrafted descriptor at this time, so on handcrafted hog at this time. So, okay. And this kind of model had a very huge success in the computer vision community. And for example, last year at CVPR, it won the best paper award for the approach having the most impact in the last 10 years in the vision community. Okay, and so now to come back to our deep learning model, the question is how can we use this kind of weakly supervised learning approach jointly with a deep convolutional neural network. And to do that, one solution and one issue is to think about how to adapt deep architecture so that we can train a deep convolutional neural network with a global label in an image and perform localized tasks. And the goal of these two slides is to make the link between what I presented before, so this notion of bag and instances, and how a convolutional neural network extracts features from images. So here, let's look at this left image and assume that you have a given feature extraction network, which is just a convolutional neural network, whatever neural network, convolutional neural network you can imagine. And what a convolutional neural network does in practice is that it transforms this input image, which is regarded as a tensor of a given spatial size and depth of type 3 if you have color image, to another tensor. And it gives you, so that's what basically a convolutional neural network does. And then you have this input image, and it mapped this input image into a tensor of spatial size L times K, and D, a depth D, which is the number of channels that you have at this stage of the network. And then if you look at this tensor, we can interpret, of course, this tensor. For each spatial position, the d-dimensional feature vector can be regarded as a description of each region in the image. Okay, so if we come back to our multiple instance learning notation, here in this tensor you have NB, which are equal to k times L, which is the number of region instances, and each instances is represented by, let's say, a deep feature that is extracted by the network, which is this, which correspond to the depth of this tensor. Okay, so once you have that, we again fall into the formalism that I presented here, where you have a given image, a set of instance and a set of feature, each instance being associated with a feature vector of size d. Okay, and now to perform weakly supervised learning, in the second way I presented before, meaning that you are able to perform classification at the region level and then pool, you adapt the architecture of the network in the following way. So you add a classification layer, which will map this input tensor into another tensor on the same spatial size, but of depth C if you have a C-class classification problem. So let's assume here that we have a multi-class classification problem with C classes. And okay, you have this mapping from this tensor to another tensor of this size, L times K times C, where each activation is now denoted as ZHC. Okay, so H is one of the instances, so there are L times K instances, and C is correspond to the prediction, the depth of this tensor, which is the prediction for each instance among the C classes. And so if you look at one slice of this tensor for a given C, it gives you what we call class activation map, meaning that you are able to assign a probability for each class of the prediction of each region or each pixel in the input image. And then once you've done this, once we have added this classification layer, we can finally add a pooling layer. And again, the goal of the pooling layer is to provide, to aggregate over spatial information, spatial region, to provide a single scalar value prediction for each class. And so at the end, the final prediction will be denoted as hat Z for each class C, and which correspond to applying a pooling function to the set of class activation map, which are shown here. Okay, and so in this problem of weakly supervised learning with deep neural network, two kind of approach, two kind of pooling strategy have been first proposed, so in 2015 and 2016, to perform this pooling operation, simply by taking the max of the score for a given class, or taking the average of the score of the activation map. So you have your network here. If you have your localized probability for a given class, and then you aggregate to get one single value for one class, and to be able again to train the model from global label. Okay, and there are limitations for both kind of approach. For example, for average pooling, average over all region in the image. So especially if you have small object in the image, is not very effective. For example, here, let's say that you are trying to detect a bottle. So your classification, your global label is bottle, and if you have a very small bottle in the image, then you will aggregate over many noisy regions which do not contain the bottle. So you have a very low signal to noise ratio. On the other hand, if you use the max pooling strategy, you only keep the score coming from one region, which is only the max, and so you only rely on one region on the image to perform classification. And for example, if you look at these two image patches, they pretty look similar, but if you put this image patch in context of their image, their whole image, it's much more easier to classify and to these two images in different classes, for example, snowboarding versus surfing, because we looked at the context of the image and the mountains on the left and the sea on the right. And the point is, of course, contextual information is often meaningful and important to perform classification. So a variant of this max pooling approach or average pooling approach that I proposed with a student, Thibaut Durand, was to combine a max pooling strategy with a minimum pooling strategy. So the idea is really to augment the max pooling strategy with the minimum value that is observed among the class activation map. The class activation map. And the insight behind this is by means of this minimum value, we are able to track negative evidence of other classes. So that's what I illustrate here. So let's consider is this left image, which is a street image from the class street on a given data set. And let us assume that you apply two different models to predict, to classify this image. One model with the street, which is the correct class, and one model with highway, which is an incorrect class. What we can see is that for the correct class, you have you have large value in several regions. But for the highway class, you also have a region that have a strong response locally, which is expected because you have a road region in these right images, and so it is expected that the highway model fires strongly on these areas. On the other hand, if you use the mean scoring region, you can take advantage of this region to drive the prediction model towards not predicting the image as highway, for example, because you have this region with very low scores, which correspond to building, for example, which are present in street images, but of course absent from most of highway images. So this is one of the main insights behind using this variant of pooling method. Okay, and to conclude on this pooling problem, we also propose, let's say, a generalized pooling function, which is written like this, which is a log of some exponential of activation map. So here again, the Z, H, C are the value at each pixel of the image, and you aggregate by computing the log of some exponential weighted by parameter beta h plus, and the same with beta h minus. And then by varying these two parameters, beta h plus and beta h minus, the interesting point in that we can recover a very popular model used in the literature from the probabilistic model, such as hidden conditional random fields, or max margin models, such as latent structural SVM, and also methods, just simple models such as global average pooling, which simply compute the average over prediction, and also the mantra model, which is based on a max plus mean pooling strategy that I mentioned previously. Okay, and so my point here about this pooling function is that when we are performing weakly supervised learning, the way you pool local prediction to get a global prediction is one of the most important aspects of your learning problem. Okay, and to finish this part about weakly supervised learning, I just present a few works using this kind of model in the context of medical image analysis. So in general, it's a formalism which is again very adapted for the detection of local pattern that are trained from global labels in medical images or videos, and for example, it has been applied for the specific for the detection of specific lesion in images with global labels, and also in this paper for the detection of surgical gesture from global labels. So imagine you have a video and you have a global label at the video level where you know the label of the video gesture, and what you are attempting to do is to localize in each frame of the video where the action took place. And these are what this kind of model are able to do. For example, here for the grasper action, you localize it at this stage of this image, and here, and for the other green action, you localize it. You are able to localize it spatially on each frame of the video sequence. Okay. One important aspect that need, let's say, adaptation to tackle medical images is to handle again high resolution images. So there have been some study on that problem to see how we can adapt the multiple instance learning problem to have to look at region at several scales. So using a multi-resolution strategy. So for example, in this work, at the end, you have a weighted average over scale of the answer of the different regions which are extracted at different scales. And there also been exploration to use some constraints which are driven by the knowledge, by the expert knowledge from the medical, which come from the medical context. For example, that is what is done in this work, where they use a multiple instance learning strategy for cancer versus lesion detection in histopathology images, based on a deep multiple instance learning approach, which is similar to the one I presented before with a max pooling strategy. Again, a multi-resolution approach, and in this work, the point that has been explored in how we can leverage additional annotation which are given at low cost as well, and especially here the method exploits the relative area size of the cancerous region, which is given as additional supervision in the image to improve performances of the model. Okay, let's say you have an additional global supervision in addition to the global label cancer or non-cancer here, which is the area size of the lesion. And it has been shown to be beneficial in terms of performances to improve the segmentation task for this problem. And in the same vein, there are also in the same context of trying to leverage some medical constraint driven in this multiple instance learning strategy. This paper, in the context of mammography classification and segmentation, propose a variant to adapt, to modify the multiple instance learning loss by using a sparse prior prediction at the instance level, which makes sense in this kind of mammography images because in general the lesions are pretty small. On average, they only occupy about 2% of the whole image. And so what is enforced during training and prediction is the fact that the model at the instance level provide positive prediction which are pretty sparse and penalizes model which will answer positive, which will assign a positive label to several regions in a given image. Okay. So, okay, I now switch to the second part. Okay. Okay.
If anyone has any question about the first part of the talk. So maybe I have a question. This approach seems similar to the masker, to the RCNN, fast RCNN network. What is the link? What is the difference between what you presented here and this architecture of deep learning?
Yeah, for this approach, so RCNN is an approach for object detection. So it is connected to this problem. So the problem is to perform object detection, but in all these models, they are fully supervised. So RCNN and all the variant faster RCNN and so on, They are fully supervised because during training you have full supervision in the sense that you want to predict a rectangular bounding box to localize the object, and during training you have the full supervision. You have the rectangular bounding box for training your model. And here the difference here that what this kind of approach expect to do is really to perform more accurate prediction. So for example, here predicting subpart of the object, subpart location of the object from this global label. Okay.
So I have a question. I think I missed a point on the basic of multiple instance learning. The second, here, when you try to learn W, or I think it's the next.
W, yeah, it's here. Here.
Yeah, I didn't make the point how you estimate the class of phi. Because you have the class at the bag level.
Yeah.
So you need to assign a class at the instance level at this time.
Yeah, but
to estimate W.
No, because what you do is that you compute the score for each instance, then you aggregate.
But how do you have W?
You train W from data, but it is trained over the max of each instance from the global label.
Okay.
Okay, so you are at the end you are able to classify each region, so each instance by this scoring function. Mm-hmm. But during training, you only take the max value of all the regions that's what makes you possible to use the global label from your bag.
Okay. And I have also a practical question from the very beginning, because I think here it maybe interests the audience about the t-SNE thing.
Yeah.
Okay, I think it's a nice tool to visualize your feature, but there is a lot of parameters if you try to get into this software. There is a lot of parameters to tune. Yeah. And my question is, sometimes if you modify the parameter, you have different visualization. So the practical question is, how do you do? Can you really compare things? Do you have to use the same parameter setting if you want to compare? I mean, for instance, two different kinds of feature set you have, and you want to compare if they are more or less disentangled?
If you would do a very quantitative comparison, you should do something like that. But in general, it's really used as a qualitative illustration of the ability of your model to disentangle classes and so on. That's what I illustrate here.
And what's your experience with that? You use a standard
my experience is I really use the scikit-learn implementation of this model with default parameters and but yeah, that's true that that's a transductive approach and a non-convex approach. So it depends on initialization. There are several parameters, so that's true that you can have different results depending on this parameter.
Okay, thanks.
Yeah. Okay, so I switch to the second part of my talk about semi-supervised learning. Okay, so the goal of semi-supervised learning is to is an intermediate learning level between supervised learning when you have label for all data and unsupervised learning when you have no label at all and you want to learn representation without label. And semi-supervised learning, the context of semi-supervised learning is to assume that you have few data, in general few data that are labeled and many data that are unlabeled. And the general goal is to try to leverage this lot of unlabeled data to improve the performances of the model compared to using only labeled data alone. Okay, and I present two main approaches to solve this task. Approaches that are dedicated to adapt the supervised learning objective function to incorporate unlabeled data, and approach that use alternative other objective function that comes from unlabeled data, for example, reconstruction, and to use this objective function in addition to the supervised learning objective, classical learning objective function. So in so in the first kind of approach, so you want to bias your supervised learning model with unlabeled data. So one popular model in the literature to do that, for example, is Transitive Svm, and more generally, the rationale of this approach is to exploit the unlabeled data structure to modify your model. So intuitively, let's assume that you have this supervised learning problem on the left. So you have 3 labeled blue point and 4 red points. And if you train a supervised learning model, a linear supervised learning model, it will find you a decision function like that. And on the other hand, if you would have unlabeled data, additional unlabeled data, which are shown here in lighter blue and red, it will certainly bias the learning of the decision function, and you would expect a decision function that falls somehow in between these two clusters of points. And really, the intuition behind this model is really to try to exploit this structure of the data to modify the shape of the decision function based on this data structure. And okay, a sub part of the approach that are interesting are approach that try to relabel unlabeled data on the training set. So you have no label for a large set of unlabeled data, and you can try to relabel each training data, and you can do that in an iterative manner. So for example, trying to relabel a given proportion of the training data in an iterative manner, and which is an approach which is connected or driven by a general learning principle, which is curriculum learning. So we can exploit this kind of curriculum learning strategy in the context of semi-supervised learning. The general insight of curriculum learning is to do an iterative training process, where you start, when you have a set of supervised examples, you start by training your model with easy samples. Okay, so it's really inspired from how we learned when you as a teacher or student when we learn something. We start by easy exercise, and then we capitalize knowledge on the problem, and then we are able to handle and to tackle more complex problems. So it's based on this kind of intuition, trying to train a model from easy sample first, and then add more and more difficult samples to the problem. So in semi-supervised learning, we can imagine there are approaches that use this kind of curriculum learning strategy in the context of semi-supervised learning, and which are based on first training a model on the labeled data set. So you have a given set of labeled data, and you train your model on this labeled data. And then you will use this curriculum learning strategy to relabel data based on the model prediction, and starting relabeling incrementally examples that are the easiest at this time. Okay, so you start from a given initialization, you relabel unlabeled data, you retrain the model for the model prediction, and you iterate. So that's a way we can tackle the semi-supervised learning problem. And I will just give a case study of a work I did last year with one of my students, Olivier Petit, which is based on this kind of approach, and what have been applied to the problem of semantic segmentation of 3D abdominal CT scans, and which is based on a practical problem that we have, because we have data, but we had data which have been labeled by clinical experts, which focus on a subset of organs. For example, in our case, we wanted to segment 3 classes of organs: liver, stomach, and pancreas. And we have a data set, an annotated data set, but in our labeling, clinical experts are sometimes have only segmented a subset of organs. For example, only the liver in a whole 3D volume, because they are not interested in segmented other organs. So we are faced on a data set with we have missing label, missing information, and say it together, say it another way, we have pixels with unannotated organs. And so in this work, we first try to train a model without any label errors. Okay, so for example, because of course, if you only use the labeling with missing label, and you are trying to segment images into 4 classes, the 3 organ classes that I mentioned, liver, pancreas, and stomach, and background. In each pixels where you have a missing annotation, if you use the background label for this organ, you have a wrong annotation labeling. So the first thing we try to do is really to remove or to remove these label errors. And to do that, our segmentation problem, we use a binary classification scheme for each organ. So for example, here we have 3 classes, liver, stomach, and pancreas, to classify each pixel in the image. And if the organ is annotated during training in the volume, because what we have is that we have some organ missing for a given volume, but if an organ has been annotated, it is annotating on all slices in the volume. Then we are able to use all pixels in the volume for learning our segmentation model. For example, in this slide, we know that the white pixels are positive and the black pixels are negative. But on the other hand, for other organs which are missing in this example, in this volume, for example, stomach and pancreas, we are not able to decide whether background pixel correspond to real background pixel or to missing organ annotation, and so we choose only to use only -1 target label for the pixels labeled as liver here. Okay, all the pixels which are labeled as liver, we know that they do not belong to pancreas or stomach, and we can only use this pixel for training. And all the other pixels are ignored during training, so that we train a model without any noise in the label. And once we have done that, we are really in this semi-supervised learning context, because we have a given set of pixels where we have label, which are certain, but we are also a pixel where we don't have any label because we choose to ignore it, so that not introducing noise in the model. And that's what we explore. We explore this improvement of the model by trying to automatically relabel missing annotation in our model by using this kind of curriculum strategy that I previously mentioned. And so basically what we did is that we start from training a model with only clean label, which is our first approach, but we did not have SMILE. And then we try to automatically relabel missing annotation in the training data set. So that was it is illustrated here. Here you have a given slice with a ground truth segmentation mask for pancreas, and at this first image is the result of the model which is trained from missing annotation, and the red pixels are the model prediction. And then we choose at each iteration of the curriculum strategy to relabel a given fraction of the top scoring pixel, which are shown in blue. For example, in this first iteration, we will label 1/3 of the top scoring pixel, which are shown in blue, and we assign to this pixel the target label pancreas, and we retrain the model with this augmented set of labels. And we iterate. That's the second step of the model. Of course, the model of the prediction have changed and improved in general, and we add an increasing number of top scoring pixel, here 2/3 of the top scoring pixel again, and we iterate until the third iteration. Okay. And what we observe is that using these two kind of approach, we compare this to a baseline approach, which will which performances will be deteriorated as soon as the number of missing annotation increases, which is a standard deep learning approach, which is shown in blue. And we show that when we have this strategy to first train without training error, we are able to substantially improve performances, and that the relabeling operation based on the curriculum strategy also help to boost performances. One nice feature that we have is that with this kind of approach, we were able to reach the same level of performance than the baseline, which is fully annotated, with 70% of missing annotation, so only with 30% of label. Okay. And so this was, let's say, the first class of methods that I mentioned, which are based on trying to exploit data structure or relabeling unlabeled example to bias the decision function. And the second kind of method I will talk about are methods which are based on defining an unsupervised objective function and then combining this unsupervised objective function with a supervised one. Okay, and the general goal of this unsupervised objective function is to try to learn representation from data, so to extract deep representation from data without any label. So to do that, the most vanilla model to perform unsupervised learning with neural network are autoencoders. So what autoencoders do, they start from an input data, so an input vector. So if you have your image, imagine that you have your image flattened as a vector. And then autoencoder map this input space into a latent space by using a linear transformation. So here you get a latent vector Z, which is the application of a fully connected layer with a matrix multiplication W. You optionally have a nonlinear function, and then you have a decoder that's come from this latent space and that's come back to the input space by having the same kind of matrix multiplication plus nonlinear activation. And to train the model parameter, what you generally optimize is a reconstruction objective that when you apply the autoencoder, you start from your input data, you map it to the latent space, then you come back to the input space, and what you expect from your model is to perform a prediction x hat, which is close to your input data. And you have a cost, which is the difference between the reconstructed data and the input data. So what you optimize is really to minimize the reconstruction cost, to optimize the parameters such that the reconstruction cost is minimized. Okay, if you have just a simple connection, interesting connection, if you don't have any nonlinear function and you have a single layer autoencoder, then it's equivalent to performing principal component analysis on your data. Okay, so this is, let's say, the building blocks of what is very standard in the deep learning literature, and then to go further to be able to express more complex feature extraction function, you can add layer. So here the autoencoder, vanilla autoencoder is a single layer. So you can add as many layers as you want to improve the capacity representation of your model and to be able to learn more complex representation. And of course, when we are dealing with images, we can also leverage convolutional network, which are well adapted to describe the local content of images and to have a convolutional and deconvolutional autoencoder. So intuitively, you have your input image. You applied a set of convolution, which a set of convolution which is applied in a hierarchical manner, which give you a latent representation space, and then the decoder will transform this latent representation space back to something which has the same size as the input image, and your goal is to train the network, the parameter of your encoder and decoder, again, such that you have a reconstructed image that is as close as possible to your input image. Okay, and there have been, so okay, in this kind of autoencoder and deep autoencoder, there have been several explorations in the literature to see what is the best learning strategy of the autoencoder. For example, do we train the parameter, the whole architecture in a joint manner, or do we train each layer, or do we do a layer by layer training? So there have been an extensive exploration of this question in the machine learning literature. And a second problem, important problem, is how can we now combine this unsupervised objective function with the standard supervised objective function, for example, classification. When you have a classification problem, you want to minimize your classification error over a training set. And a simple way to do that is simply to define a combined objective function, which is, for example, simply a weighted average between a cost function based on classification, which penalizes your model when your prediction is wrong compared to the supervision, and a reconstruction error, which comes from unlabeled data, which penalizes when the unsupervised objective is unable to properly reconstruct data. One important point I want to highlight today is that this kind of reconstruction cost, which is the basis of for training autoencoder reconstruction or maximum likelihood, let's say, which is the basis of all this deep autoencoder model, is somehow questionable. And one open question today, nowadays, which is asked at the community, is it a good idea to use reconstruction for unsupervised learning? And one question, one issue is the fact that when you want to use this reconstruction objective function for unsupervised learning, in general, your ultimate goal is not reconstruction, of course, and in general, your ultimate goal requires some form of generalization to a set of examples. For example, if you want to use this unsupervised cost for improving a classifier performances, you want to perform classification at the end, and when you perform classification, you want to generalize to a set of examples. And the point is, when you build deep representation as well, the insight behind the hierarchy in the deep neural network is to gain more and more abstract representation when you go up into the hierarchy, and then to generalize to a lot of example, and say it another way, to lose some information somewhere. So when you lose some information, you are not able to reconstruct. So somehow these two objectives, classification and reconstruction, they somehow play contradictory roles, because if you want to classify, you want to generalize, so you are not able to reconstruct anymore. And if you want to reconstruct, you need to keep all information from input data. So this is an important issue, and the point is, one common strategy that has been used for semi-supervised learning with deep autoencoder is to use a model, a joint model, which is able to perform classification and reconstruction. And my point is, both tasks are somehow contradictory, and if you use a single model to do that, there is a risk that the unsupervised objective will try to keep too much information for the supervised one. And I present now, to finish this presentation, two kinds of approach that try to go beyond this reconstruction objective function for unsupervised learning. So approach that design objective function that relax this reconstruction constraints, and approach that are based on a different learning strategy that try to transform the unsupervised learning problem into a supervised one. So one popular approach for one important model for which maybe was the first approach that tackled this problem, to try to learn autoencoder without imposing a strong reconstruction cost, are ladder networks, which have been published in 2015. And basically, I think it's a quote from the paper, a ladder network can be regarded as an autoencoder which can discard information. So again, it's really the insight that I previously mentioned. You want to design an autoencoder, but you will not. Your objective is not to enforce that your latent space is able to reconstruct your input space. So you want to you enable your model to lose information somehow. And in ladder network, basically what you do is that you impose for a given layer at a given depth of the network, you do not impose the layer above to be able to reconstruct the layer below, but you add additional information to that, and in particular in this model, they add a noisy version of the layer below to be able to reconstruct the layer below from the layer above. Okay. Another approach in this direction is something I proposed last year with the student Thomas Robert, and which is a modification of a deep autoencoder, which is a variation of the architecture, which is called a hybrid net. And basically, the general motivation is really to try to disentangle the information between what is required for supervision and what is required for reconstruction. For example, in this example, just to highlight the general ID, here you have an image with a digit. So it's an image from a public dataset in the literature, which is called MNIST-M. So it's a variation on the standard MNIST dataset handwritten digit, but you have texture or color superimposed in the images. And if you want to use this dataset to perform digit classification, so you have this image. Clearly, there are some part of the input data which are important and relevant for the classification task, and others that are not. And in this case, clearly, parts which are relevant are the shape of the digits. So this kind of feature is important to classify and to discriminate this image from other digit classes, and all the color and the texture which is superimposed to the image is not relevant for the classification task. So again, if you use a reconstruction objective that tries to keep all information from input data, you are somehow disturbing your learning process with noisy information and irrelevant information. So what we propose here is really to split the prediction into two branches. One branch which is dedicated to the classification. So for example, here you have a bird images and you want to perform a classification. And you have an encoder that will predict the class. And then to reconstruct the input image, we add another encoder which intuitively is dedicated to capture the information which is lost by this first branch. And again, as this first branch is driven by classification, it is supposed to lose some information because you want to generalize to a class of concepts. So in this branch, you expect to lose some information, and in the second branch, you want to recover the information that is lost by the first branch and to be able to properly reconstruct the input data. So using these two kind of architecture, we show that we can improve performance of the semi-supervised learning algorithm. And one interesting point that people recently explore this idea for segmentation of medical images. So it is a paper published last year at MICAI, and which is based really on the same insight, but applied in the context of segmentation of myocard images. And so the author of this paper observes the same phenomena that I previously mentioned on the fact that reconstruction and classification are somehow contradictory. And for example, here, if you use a baseline semi-supervised learning model that tries to combine reconstruction and classification, what they claim and what they highlight here is that depending on how you weight classification or reconstruction, it's very difficult to be good at both tasks. For example, on the left, you have the input image, and if you weight too much and you have a very large segmentation learn, you have a very large segmentation loss. You are very good at segmentation, that's the middle image, but you are very bad at reconstruction, that's the right image. On the other hand, if you weight too much the reconstruction loss, so you have a very large reconstruction loss as shown in this right image, you are pretty good at reconstruction, the right image, but you are very bad at segmentation. And in the same spirit, they propose a two-branch architecture, which is called SDNet, and which is dedicated to split the information into one branch, which is dedicated to performing segmentation, so to extract class-related information, and one other branch, which is dedicated to extract a global feature vector, which describes the content of the image as all the information that is lost by this segmentation branch, and how to combine this the segmentation mask information with the complementary information to reconstruct the image and add this reconstruction cost with these two branches. Okay, and they perform some nice visualization of the ability of their model to disentangle supervised information. They also report some nice, let's say, arithmetic operation that you can perform in the latent space, something that is common in the embedding literature. And they also show that they are able to significantly improve performances in the semi-supervised learning context. When you decrease the number of label images, their approach is able to leverage unlabeled data to keep at a certain, at a constant level of performances, whereas the baseline approach, which is only based on label example, performance drops significantly. Okay, I have 10. Yeah. 5 minutes? 5 minutes? Okay. Try to be short. Okay, I'll just give the high-level overview. I think that's interesting last point, so that I will be short. So the last option, I think it is extensively explored at the moment in the machine learning and vision literature, is again to try to design unsupervised learning model that go beyond reconstruction, which are called self-supervised learning. So the general objective of this approach is to transform the problem which is at the beginning unsupervised to a problem which becomes supervised, but you build supervision automatically from your data. So the goal is to train a network to perform prediction tasks on data, directly on data. For example, this is one example. There are several ways several solutions to this problem, several approaches to tackle this problem, but this is one which have been proposed at the computer vision in the computer vision community. For example, you want to train a model which predicts the relative position of different regions in image. For example, if you give you this region, which is the nose of the cat and the ears of the cat, you want to train a model which is able to recognize that the ear is at the top right of the nose. So you train a model based on that, but to train the model, you don't need any label, you only need data. And that's what we call self-supervised learning, because we have converted the problem which has no label in a problem when you have label. Here we have a label, you have label data, but that have been built automatically from your data without manual supervision, human supervision. And then this transformation from an unlabeled problem to a labeled problem generate what we call an auxiliary or a pretext task. So in this case, the relative prediction task. And the feature that you learn from this task can be used after for representing your data and for adapting in any supervised task. Okay, so that's the general idea. So I mentioned several auxiliary tasks that have been observed in the literature. So I will be short, but if you have any question, I can detail a bit some of the approach. Maybe one of the most famous approach in this category come from the NLP community and is Word2Vec, or all the word embedding approaches, where the general goal is to have a word as input and to train a model which is able to project each word into a vectorial space, a dense vectorial space. And to do that in this kind of embedding method in Word2Vec, what you train is that you try to predict a word given its context. For example, you have a text. You look at the surrounding words and you want to predict the central word given its context. So it's how the model is trained, and again, it's trained without any manual supervision. So that's, let's say, the most famous approach in this category. And this kind of insight has also been applied for images, for vision, with the same insight. For example, here, the auxiliary task in this paper is to predict a given patch which is missing in an image from its context. So your self-supervised learning problem is, I have this image without the white square, and I want to predict the visual content of this white square from data. Again, without any manual supervision, but only leveraging data. So the auxiliary task is to solve an in-painting image processing task when you want to fill holes in the image and performing predictions such that you are able to fill holes in this image. Generative adversarial network are other kind of approach. The next course will be about that, but it's another kind of approach that are self-supervised in the sense that they try to generate data by transforming a problem which is unlabeled at the beginning, but by using supervised model with the generator and the discriminator. And to finish, two other examples of auxiliary tasks that try to be more and more used in the vision and medical image analysis community. First task is image colorization. The first thing I forgot to tell, but which was on the slide, is the main purpose, what we expect from the auxiliary task. One important feature that we expect in the auxiliary task is that the auxiliary task must solve vision problems that are complex enough, that require some complex and semantic task. Okay. For example, image colorization. Here, the problem is you start from a gray level image and you want to predict the color images. And basically, to train that, it's pretty simple. You have an image color data set, and you only convert it to grayscale, and you try to repredict the color image for each input image. And the point if you want to perform this task, the insight behind it, why it works, why training representation based on this task works, in that for solving this recolorization task, the network somehow must solve high-level recognition problems, such as detecting certainly object or parts, or detecting a region and concept in the image for performing this colorization task. Another auxiliary task it consists in predicting. You have an image and you want to predict the orientation of the image. For example, here it's a vertical image, here vertical but in below, and so on and so on. Again, to perform, if you have an image and you want to predict the orientation of the image, certainly you must be able to perform object detection, object recognition, and some complex tasks. And then you must encode important feature for solving this task. And to finish, in particular, this kind of colorization, recolorization, self-supervised objective have been used for endoscopic video colorization as a pre-training step for extracting feature for endoscopic video colorization, really based on the same objective approach. So you have endoscopic video, and you extract for each image a color map in the LAB space, and you want to predict the color space from the luminance space. And it gives you a way to extract representation for your data. And what they show in this paper is that based on this representation that can be trained in a very large volume of unannotated data, then you are able to improve the performance of some supervised tasks, for example, segmenting instrument in this video data sets. Okay, so I'm just to conclude and as a conclusion. So what I've talked is about the problem of annotation. So the collecting huge annotation is a big problem everywhere, but I think it's especially important in healthcare and medical imaging. And I presented two kinds of approach to solve this problem. So learning from weak supervision, so coarse label. And what I mentioned is that the pooling function is one of the crucial, of the most important element of this weakly supervised learning model. Okay, and when applied for medical image analysis, I think interesting aspect that have been explored is how to constrain the model by integrating some prior knowledge about medical image. And regarding semi-supervised learning, I mentioned two kinds of approach. The first one, which were based on a automatically relabeling example, for example, based on a curriculum-based approach. And the second main take-home message is that there are many open questions nowadays about trying to define and design objective function that goes beyond reconstruction that have been the main objective function for unsupervised learning since 20 years. Okay, thank you for your attention.
Does anyone has any question on this talk?
Hi, nice presentation. I have one or two questions. Maybe we can go back to the curriculum learning slides. Here, I thought that curriculum learning was a method that starts with a fully annotated data set, but then during the first epoch, you just select the points that are easily separable, and then after a certain time, you start adding up more and more complicated elements.
Yeah.
Isn't it the case here, or is it that your data set is not fully labeled, and so you first train it, and then you use unlabeled data to eventually refine the model?
Yeah, that's it. That's what I mentioned. In general, that's what we said. In general, curriculum learning, for me, is more you have a fully labeled data set, but you want to start by training with easy example, and you want to train a model incrementally by starting by easy example and adding more and more complex example incrementally. And here, what I propose, and I see several papers that use this kind of approach for handling semi-supervised learning, and the general scheme of this approaches consists in first training a model with only labeled data. So you have labeled data and unlabeled data. You firstly train a model with labeled data, and then incrementally you will try to relabel unlabeled data based on the current model.
In that sense, what is the difference between curriculum learning and active learning? Or maybe it's the same?
No, active learning, I think it's how you perform active selection. I think active learning is more general because in active learning, you want to active or interactive learning. You have a first model and you want to provide example to be labeled, a subset of example to be labeled, and one main question in this active learning problem is what selection policy do you choose for labeling your data?
So here there's no selection policy, it's just randomly.
Yes, the selection policy would be I will start by the easy example and add more and more complex over time. In general, in active learning, you are more interested in selecting uncertain example, so that's not exactly the same context.
Okay. And the other question that I had was regarding the model that you published that was using autoencoders, either to do labeling. There was a picture of a bird. Oh, yes, this one.
Yeah.
Or the other one. In what sense this method uses semi-automatic data, semi-labeled data set? Because my impression is that you need to have the labeled bird in order for this system to get trained. Is it that in some cases you don't have the label, so that way you can still train the autoencoder which is on the bottom?
Yeah, exactly. It is dedicated to semi-supervised learning. So again, you have very few labeled data, and on this very few data, you train your model to correctly predict the class label.
Okay.
And for all data, you have the data themselves, and so for all data, you are able to compute your reconstruction cost.
Okay.
And what we show is that using this additional unlabeled data, we are able, with this kind of model, to improve performances compared to a model that only use labeled data.
Okay, thank you.
Yeah.
Following this question, on the next slide, on the medical application, you show just before the performance here, as a function of the number of labeled images. So, well, this what percentage corresponded? I don't know. When I see 11 image, do you know how? I want to know the percentage of unlabeled versus labeled images for this performance. Is it 11%, for instance, here?
I don't know.
You don't know? I was just asking the how how does it perform when you have very few labeled, when the percentage of label instance, label image is very. Is it working with only 1% of label image, or it has to be 20% of?
I think it's already very few at this stage. I'm not sure. I think we have to check on the paper, but I think it's already very few because in ACDC I think it's a pretty large data set. So yeah, I think it's just a number of label images. I think so. I have to check. But, okay. To me, what my guess is it is a number of label image. So,
the total number. So
maybe. Yeah.
Okay. And again, when you come back when you train your model, so you have the two losses, the label one and so there is a hyperparameter lambda between these two losses. And when you train, how do you input your when you select your batch? Is there any strategy to mix the labeled and unlabeled image in the mini batch? I don't know. Is there?
Yeah, I mean, we do not do something very very specific to this problem, but of course you need in each batch to have label and unlabeled data, and we keep the ratio between label and unlabeled data constant in each batch, something like that.
It's okay, but there is no rule of.
No. It's as in standard multitask learning problem. You have to combine objective function and to weight them properly, but yeah. It's more or less ad hoc in the sense that just you have to look at your how your training progress, how your two objectives cooperate. And,
Okay, thank you. Some more question?
You mentioned several auxiliary tasks for the self-supervised learning.
Yeah.
Is there any rationale on how to choose the task or the auxiliary task depending on the real task you want to solve afterward?
Yeah, as I mentioned, the main insight behind all auxiliary tasks is that a good auxiliary task is a task which requires to solve complex and semantic problems. So, for example, performing object recognition, scene recognition, and if the auxiliary task requires such complex things, then certainly the auxiliary task needs to extract relevant representation from data for another semantic task. And all the strategy I mentioned somehow fulfill these requirements. So,
is there any preference to choose one or the other? If you do, I don't know, segmentation after what? There's no...
No, I don't have clear insight about that because, really...
Any more questions? So I guess we can thank the speaker.